Hey, this is XDF, and with Cyber Apocalypse coming up later this month, definitely go sign up for that. It's gonna be a lot of fun. I wanted to find a challenge from last year's Cyber Apocalypse and spend a little time make a quick video on it. So, I've been scanning through the track. You can come on here. Let's see, somewhere in tracks, um, and there is a 2024. Let's see if I can find it. Was not planning on doing this, but somewhere in here, Cyber Apocalypse CTF 2024. You can click in here and see all the challenges from the Cyber Apocalypse last year. And I've been sort of just scanning through these, looking for one that might be interesting. Reversing kind of caught my eyes. I haven't done much reverse engineering lately since Flare on last fall. And this QuickScan got me because it's on the easier side. But it looks like it has some interactive components to it. So in order to escape this alive, you must carefully observe and analyze your opponents, learn strategy and techniques in their arsenal. You will stand a chance to outwit them, do it fast before they do the same to you. I don't know, it's kind of meaningless, but there's some interaction, and I've spawned myself an instance here. So let's go ahead and take a look. If I connect here, it says, I'm about to send you 128 base 64 encoded ELF files, which will load a value onto the stack. You must send back the loaded value as a hex string. You must analyze them all in under 120 seconds. Let's start with a warm-up. All right, so I've got a base 64 encoded string that says ELF. I've got expected bytes and it's asking for bytes. Before we play with the file, if I pass it something different, it says incorrect, try again. If I pass it the correct, okay. So that didn't work. If I connect again, I can see it's a different ELF, a different length. And let's see, so if I just put in the expected bytes, it says, okay, we start for real. There's the ELF, and presumably it's not the same. Too bad, took disconnects. So I guess I'm gonna have to do these in a program. So I think there's gonna be two parts to this. I'm gonna need to reverse engineer at least. I'm gonna take these first two and create files for them, look at them, and see how similar they are. If they're very similar, I'm gonna try to then move to part two where I create a script that can take this base 64 string and return a hex string or send it back to the server. And then I'll just run this in a loop until it either gives me a flag or till it fails, and then I'll have to look at another one manually and see what's different about this binary that it didn't work and move from there. So, all right, we got a plan. Let's see, I'm gonna start with this. Let's say, let's go to a new terminal. I will echo that into base 64 minus D into, what do I call this? Warmup. And then let me grab this other one. And if I do echo that into type in a base 64 minus D into ELF1. All right, let's see if we do file on both of those. They are both 64-bit ELF executables, so that worked well. They're small. They're both, under 1,000 bytes, so they're pretty tiny. What else can we do? Yes, we're probably gonna need to go into Ghidra, or we can go into GDB. We can try GDB first. If I do GDB, oh no, I don't want that. On not tab completing. Oh, I gotta change mod plus X star. Now I can do GDB on start with warm up because we at least know what that one's supposed to look like. If I do info functions, oh, actually, before I even do that, what happens if I run nothing? If I run ELF1, okay, so nothing there. Let's try it in GDB. Info functions. No, there are no functions. All right. A trick I learned not that long ago. If you run start I in GDB, it will run to the first user-defined instruction and break there for you, which is actually incredibly convenient when you don't know the entry point. We could get the entry point. We could do let's see, it's readelf. I always forget which one. What I'm looking for here. Funny, I put in -H, but actually that's what I was looking for was file header. So I was trying to do help. That's not what I wanted. If I do that on warm up, so we can see the entry point right here is 804.822C, and we actually are at 804.822C. So that start I took me right to the entry point, right where I wanted to be. Let's see, we can do X. Let's print out like, I guess I'm gonna really need to open this in Ghidra, aren't I? I can do X like 20i to get the next 20 instructions from this point. I don't think I need a star there. No, I don't. So I can kind of get some disassembly here. I have no idea what that looks like. Gobbledygook. We're gonna come back. We're gonna have to go to. We're gonna have to go to Ghidra. Let's see. Open up another one here. Let's do Ghidra. And booting up. All right. Close that. I've got a different. Let's open a new project. And the location will be home. QuickScan. I like to always just create a Ghidra folder and make that the project directory. Project name will be QuickScan. Cool. And then we can import some files into it. Let's see, home, QuickScan, warmup. Okay. Okay. In fact, let's go ahead while we're here. We can import the file elf1. And okay, so if I go to warmup, see what we got. Hopefully this will be more useful than what I saw in GDB. Yes, we will analyze it. We will use the default analysis. You look down here in the bottom right for a status bar. Usually that takes a few seconds. This was so small, I'm guessing it's just finished. And we have one function, the entry point. Let's see what we got here. Let's see. It looks like so it's got some global variable. So it's gonna get the address of this global variable. It's going to loop over. Let's see, for 8. So I'm gonna rename. Let's do some renaming here. So that's an I. So for I is equal to x18, which is 24. It's going to, well, I is not equal to 0. It's going to loop and subtract 1 each time. It's going to copy from var1 to var2, which is on the stack. And then it's going to increment both pointers and continue. So it's going to copy 18 bytes from this buffer to the stack. We go here. I say 18, 24, depending on how you want to look at it. Oh, we can actually look at these right here. 8920 F8. Let's see where we were in 8920 F8. So that is definitely it. So we need to be able to read this binary, get this this address right here, and figure out how to then basically read that many bytes, OX18 bytes from that buffer, and that's gonna be our answer. Look at this a little bit. What does it do? We can look at the assembly because we're really going to need to do some some programmatic disassembly here. So the first one is just, this is basically creating some space on the stack for us, creating OX18 bytes of space that's going to be for that buffer on the stack. And then we're going to load effective address here. We're going to move there, and we're going to do this. We're doing it here. In fact, you can even see the bytes. Are these the bytes right here? Starting right after? It's clear to me. I already forgot what the answer was, so. Or are they up here? I bet they're up here. It doesn't matter. What we need to be able to do is this load effective address. We're going to need to understand this instruction. And so this instruction, 8D is the, I think if I remember correctly, 48 is like a 64-bit indicator. The important thing here is this offset right here. I bet, let's see. If we do, Python, OX, FF, FE, 44. And how do I make that signed? I think I need to do minus OX1, FF, is that right? 444, let's go with that for a second. And that would be subtracted from, I think it's the one after here. So let's see. 80, 48, 237. 48, 237 minus 444 is 7793. Oh man, this is hex. That is not what I needed. Let's see. OX. And we want that in hex. 804 87B and 87B. Yep, that's it. So that was, in case that was kind of me fumbling through it, so I'm gonna go through it a little more clearly for a second here. If I go back to this load effective address right here, where I'm loading this buffer, the global buffer that has the value I need, into RSI, what I'm doing, or I guess the address of that buffer technically, the last 4 bytes give me the offset from the instruction pointer. And so the instruction pointer at the time this is running is actually moved on to the next one. So that's where I get my 80, 48, 237. So I'll have OX 80, 48 to 237. That's the instruction pointer. Minus, and then I'm going to have basically what is FFFFE44, which is, you can see from right here, negative 444. So negative 444, and then I just to display that as hex because that's what we're doing, and that came out different, probably because I typed in that incorrectly there, and that gives me the address. Cool. Okay, so I can do that. Let's see if we can do that programmatically. Well, I guess before we go too far, let's now take a look at. I'm gonna go ahead and save you, and come back here and open up elf1. Because if elf1 is completely different, there's no point in writing a program yet. I mean, how I write my program is going to depend on how similar these two are. Now, that doesn't mean that couldn't change over the course of 128, but let's at least start with this, because this is all we can see right now. All right, and we in elf1, we are. It looks exactly the same. Copying 18 bytes from this offset. Okay, well then at least we can try that. So let's come here. We will do, open this in VS Code. And I don't need you. All right, you do need me? What do you need my password for? Do I trust the authors? Yes, I trust me. We can close this. This looks very tiny. Let's see if we can get this bigger so you all can see it. Close a welcome. Let's see, we'll call this solve.py. Very creative. From pwn import star. We're gonna use PwnTools because it just gives us the ability to connect to the remote server, read some stuff, do some stuff, etc. So probably gonna need to create, let's see. We will do Python -m venv. That's gonna create ourselves a virtual environment. I want to start learning UV. I've not learned it yet, so we're still doing it that way. We will source venv bin activate. We will pip install PwnTools. Boom. Hopefully this is going to recognize a virtual environment's been created. Do you want to use it? Yes, we do. And now we should at any second have PwnTools. I'm going to have to, if this doesn't go quickly, I will pause and zip through. Awesome. Okay, so we got that. So now I can say from pwn import, I can say remote equal, let's say r equals remote. I think there's a way to do this in PwnTools, but I'm not sure off the top of my head, so I'm just going to use sys. I'm going to say sys.rgv dot sys.argv dot 1 dot split, because HackTheBox gives it to me there. I think that'll work. Maybe I'm going to make this a tuple. And then we can r.interactive. We're just testing to see if this works. So now if I open up a thing and do Python solve.py, clearly needs a thing. Let me go grab my window back here, paste you in, and it's missing an argument port. That's interesting. I feel like this shouldn't be that hard, but now we get to watch me go into a rabbit hole of how do I make this string? So if I do that dot split on you, and I want to make that into a tuple, and then maybe I just need to do remote around that. Name remote from pwn import remote. Missing argument port. Well, that's weird. Why is it missing a port? Do I need to untuple that? Oh, do I need? I'm back. A lot of the Python stuff by default takes a single tuple that contains both, and I think I'm like doing the opposite here. So what I really want to do is that is the wrong place to put that star. Is put this star right here, and that connected. And what do we get? We connected. Do we get? Let's do. Oh, I didn't even save it, so I don't have it anymore. Okay. Okay. So what I need to do? Sorry, I'm getting distracted here. We will do that. I bet it will work. Let's see here. Python solve. Boom. Okay. So we made progress. Excuse me, fumbling for a second. We now can read this here. So what I want to do, I don't want to just go interactive. What I want to do is I want to say r dot receive until, isn't that until? recv until, perfect. And we'll put our bytes here, and we want to go basically that right there. And then we will say elf equals r dot receive line, because it's all one line. That'll give us our thing. We're going to need from base 64 import b64 decode that. So now we can say receive line b64 decode like that. And let's try running this and see what happens. So if we run this, say print, actually let's write it to a file. So we will with open, I could do this with like dynamic buffers in Python, but I'm just going to go ahead and open it up here for now. We'll call it ex1 write binary as f dot write elf. Now if I connect this here, and if I do file ex1, I've got an elf. Awesome. Okay. Now let's see. So what we need to do here is we can now say e equals elf of ex1. We're obviously gonna make this more of a functional thing later, but right now we're just sort of doing a proof of concept. Can we pull this out? So we create an elf object with this. We can print e dot entry point like that. Let's run it again. Oops, no, let's run this again. And we switched to interactive mode. We did not print, interestingly. Did I not save this? Oh, not sure. Let's see. What if I get rid of the interactive? It might be chomping me. Oh, there it is right there. It's printing the, was it printing it there every time? It was. So I'm getting the entry point from there. That's good. Now we wanted to get, let's see if we can get that load the LEA address, right? So that is going to be LEA address is going to be e dot entry point plus 4, I believe it was. Where's mine? Click here. So the first thing is this 4-byte subtract, and then the next one is right there. That's what I want. Okay. The offset of, let's say buff offset is going to be LEA address plus 3. In fact, let's go ahead and read that. So we can say e dot read. So we're going to read out of the thing, and we need a count of 4 bytes here. Let's see. We can log dot success got LEA address, and then this will be hex LEA address, and then we can say, so this is going to give us, I'm gonna do another log here because I don't think we're on the right format yet. Got buffer offset hex buff offset like that. So let's run that and see what happens. Bytes cannot be represented as an integer. Let's see, what did I get wrong here? So, okay. So this right here is going to read 4 bytes for me, but I want to turn those 4 bytes into an integer. So I'm going to unpack 32, and this can take, I want it to be signed. So I'm going to say sign equals, I believe I just put, oh yes, signed or unsigned. It's on the screen right there. So we'll say signed. Now run this. We got the buffer offset of, interesting, it's in the positive direction. Okay, that's fine. Is that always the case? I thought it was negative for me, but it seems to move all around and mean positive or negative. We'll go with it for now. Okay, so now that we have that offset, we're going to need the actual, I guess the actual address is, let's see, so, didn't mean to do that. Buff address is going to be RIP, which is going to be the entry point plus, let's pull it back up here so we can look at it. It's going to be this entry point. It's going to be plus 4 to get to here, plus 7 to get down here. So it's going to be entry point plus 7. Plus 11. So it would be entry, e dot entry plus 11. We'll make it 4 plus 7 to show that. Plus the offset. I don't know why okay. And then we should be able to do values is equal to e.read. I'm just going to assume for now we're always reading 24. And so we're going to do buff address 24. Let's log.success values. Give it a run. Well, there it is. That's garbage though. It's really hard to not what I want. Let's do. I think we can, if it's bytes, we can just make it .hex. Awesome. So let me do one more thing. Now I can do r.interactive and run this, and we can see we printed out this string, and that is the string expected. That is beautiful. So let's see what happens if we do r.send line values.hex. That gonna work? It might work. Now we start. So that worked. So that worked beautifully. Okay. Now let's turn this into a loop. So let's see. What do we want to do? Okay. I'm going to say, let's make a function. Get def get hex from base 64. Going to take a B64 string, and it's going to return, well, I'm not going to worry about typing for now. It's going to do all of this. So let's see. We're going to take u. We're going to get rid of a lot of this logging because it's doing it 128 times. We're not going to be so loud. Okay, so we're going to with open. Okay, so we are going to with open elf. I guess we're just gonna call, this is dangerous. I should really name these things different each time, but I'm gonna go for just naming them the same. I'm gonna write, what am I gonna write to here? I'm going to write B64 decode B64 string. Then come on here and we'll say this is elf. We're gonna open it up, and then we can, I'm gonna grab all the way down to here. Oops, didn't mean to do that. We'll just tab it in. Okay, so we load it as an elf. We get the entry point. Get rid of u. We're going to read in the offset. We're going to read in the address. We're going to get the values, and we're going to return values.hex. Now that is our function to get hex values from a base 64 string. So now we'll say we'll get our remote. We will for underscore in range 128. And I think we might need to go 129. I'm gonna do 129 because I have to do, because the first one maybe is not very good, is the test one. So we're going to receive until we get elf. We're gonna take that receive line. We're not gonna do, we're gonna get rid of all of you. We will say result equals get back from base 64 of elf. Oh. Maybe, oops, I didn't do that. Let's see, we'll get rid of you. Maybe we'll call this, oops, rename symbol. We'll call this base 64 string. So we pass it in there. We will get the result. We will send the line for result. And let's give this a shot. I'm not sure if, I'm not optimistic it's going to totally work, but it'd be nice if we had some sort of update on how we were going. Maybe I should do a print in here. We'll do. I'm not even sure. Are we working right now? Like presumably we could be, and we got the flag. So maybe not. Maybe we didn't need to worry about that. So apparently all the binaries have this same rough format, and we were able to solve it this way. So this was a good, like, not, the reversing really was not that hard. It was almost more of a programming challenge, but being able to go in here and sort of understand the assembly well enough to know where the buffer was and where how you could load that address and then get it and print it out is really the key aspect here. So Some neat tools that will come invaluable, hopefully, if you do any pwn challenges or maybe some reversing challenges in this year's CTF. So thanks for hanging out with me today. I hope you enjoyed this. Thanks so much for staying till the end. It's one of the best things you can do to support my channel. And I'll talk to you next time.